Please just inform how it is.
For the next slide and this complete. Okay.
Pointers. Put it on the screen. फर्स्ट स्लाइड तो चला ऑफ कर लो डिट फॉलो माइक
Good morning, everyone. Am I audible?
Yes, sir.
Okay, before I could start my lecture, I just wanted to tell you the spacecraft operations is a little bit a complicated one because you have to operate the spacecraft without seeing it or having it. As an example, I can tell you, we can travel in a car. If the car gets into a problem, you can call the mechanic and then get repaired and then you can continue. Whereas this kind of a thing I can't do to the spacecraft if it gets into a problem. Okay, that is the main challenge in keeping the spacecraft alive, and then it should be kept in its conditions, environmental conditions, so that the satellite can be made use by the users. Okay, I will just one more. Yeah, so that's how what I have chosen. The topic is spacecraft mission operation, challenges and mitigations. So I have just you can reach me on this mail ID. Okay, whatever it is, you have the doubt, you can come back to me. So generally, when I start my rather lecture to the students, like our Guru Vandan, I used to put this slide. Oh, come on, what happened? It is supposed to be a
Video. Video frame.
Not video. It's supposed to be coming with audio and that's what I told you. Okay, fine. It's all right. Okay. No. Go back. Audio file you just connect. It's an animation file. Okay, leave it. Don't worry. Okay, so when our space father Vikram Sarabhai represented in the UN Council, the other country people were asking him, India is a developing country, can it have such a high technology? Further, the answer given by him, I have just reproduced there. There are some who question the relevance of space activities in a developing nation. If we are to play a meaningful role nationally and in the community of nations, we must be second to none. That is what is a statement, and it should be useful to the humankind and the society. That is what is thing. So with this, I'll how we started our program in 1963. It was started in Saint Magdalene Church, which is in Trivandrum. Now that is converted as a museum, and then you can have, of course, these two figures you will be keep seeing everywhere. So this is how we started our space program. Okay, see, we were not having any sophisticated vehicle and all in those days. Actually, we are supposed to do all these things in a rather separate special vehicles are there, but those days nothing was there. So they were taking the sounding rocket things in the cycle. This is how our beginning. In 1969 we were, and then in 1972, this was the status of our Bangalore Satellite Center. In Peenya Industrial Estate, they hired the industrial sheds and converted it as a satellite building center. So when Russians, my seniors used to tell, when Russians visited, they were jokingly asking our people that, are you really serious in building a satellite, or just like that you are doing? But we did. In 1972, they started the project. In 1975, they launched the satellite. See, that is a question. That is the kind of intelligence and the knowledge and the kind of dedicated work what we have. Of course, this bullock cart, many people used to wonder how it is this and all. It is mainly, many people may not be knowing the actual background by this. When the satellite is being built, we used to test in all its aspects in the ground itself before it is launched. So, in that time, we are supposed to do the RF interference test. For that, we need an open field, and the satellite needs to be moved from the integration to the field by a non-conducting platform. Now we have crores of rupees, and we have the vehicle and all those things. But I am talking about in 1979 and 80 time frame, we are not having that much amount of money, because the entire project, Apple, where I joined, the entire project cost itself 14 crores. So then what, one of our senior, when we were discussing what to do for the transporting, then someone has suggested, why not we use bullock cart, because it is made up of wood and it is non-conducting. Then that was implemented, and the satellite what you are seeing, the same one tested and it flown and it worked for 3 full years. Why I am telling this is, whatever we have done, it is with the available resources. We were not waiting for resources. That is what. And the next one, our working culture. You see, I think most of us, most of you will be knowing Dr. Kalam sir and Aramjan sir were there. They were the actual project directors for the sounding rocket, but you just see what they are doing. They are doing the bolt and nut things. See, that is the kind of a work culture. Don't wait for anybody. If there is a need, yes, get into the field and then do the work. That is a kind of a work culture, and that is how we, our space is doing so far, so good. That's it. Okay, now we will come back to our main discussion, mission operations. What is mission? Okay, if you take the dictionary meaning, it is an act of setting somebody to perform a specific task. Okay, whereas in our reference, this term covers everything, including design, fabrication, testing, launch, operations, and then it is supposed to meet the objectives. Okay, that is the main thing what we are looking for. The mission perspective, I just wanted to tell you. There is an objective, because without any objective, we can't do anything, or just like that, also we cannot do something. So that's why. Once the mission objective is known, what do we do is, first thing in our we plan the mission. That is, what are all the things required. Then from there, we will derive the mission requirements, because based on the objectives and the planning, we will derive the mission requirements. This is the very basic thing for any spacecraft mission. We will be doing it. Further, yes, lot of mission analysis work is required. So based on the analysis, the feedback will be taken, and again it will be checked up with the objective, and then we will see the planning aspects, and then finally we conclude, and then we finalize the mission requirements. In a broader level, it is not that nothing is being done 100% in the beginning itself. It is an evolution process. So once this is over, okay, next becomes a mission architecture. That mission architecture comes into 3 segments. One is ground segment. That is where that tracking and all other aspects. Then launch system. This is mainly how the satellite spacecraft is going to be launched. Then the space segment. That is the satellite itself. Okay. Next comes is our mission operations point of view. There again, it is the software required, the documentations required, and the kind of network support. That is that worldwide we will be having the tracking support kind of things. So with this, these are all the main rather broad guidelines for the mission perspective. That is, if you go through from mission objectives, we derive mission requirements. Based on the requirements, mission architecture has been done. That is nothing but satellite and the launch vehicle as well as the ground system. Then comes the mission operations. Okay. Then a typical spacecraft mission cycle, because why I am going a little bit in a fast track is because we will see the challenges and other things. There we will a little bit more we will elaborate. That's why, because these are all the standard things. Once you know the mission requirements, you go for the required mission analysis, and then the design studies. That is, after having the things, what are the possible designs we can have, and then how to go about it. Okay, that is where that design studies will be coming, various options, and then we will see, and then based on the things, how optimally we can build the spacecraft. That is the main thing. Next comes development and verification, because once you can have something, but it needs to be verified finally after realizing everything. If it is not meeting our objectives, then the entire exercise will be a waste. So at every stage, we used to verify whether things are in order and are we following the things and all. Okay. Then comes the pre-launch exercises, because once the satellite is launched, prior to the launch, we'll have to have some kind of compatibility studies with the launch vehicle, and in the launch site, what are all the exercises will need to be done, and how the data flow is going to be taking place, and how it is going to be connected to the control center, and all those things will be coming in this pre-launch exercises. Then launch plan activities. That is, at what time, what needs to be done, and how are we going to interface, because it is 2 different teams. Launch vehicle is one entity and satellite is another entity, and the launching agency is the other entity. So all the 3 entities needs to be coordinated, and then we'll have to make a plan, and then accordingly we'll have to execute it. That is how that launch pad activities will be coming into the picture. Then comes the initial phase operations. See, once the satellite is launched, of course, launch vehicle job is over. It has done its job. Then we'll have to take it up, and then the spacecraft, it needs to be tested in all its form. Sometimes, like a geo kind of a spacecraft, it needs to be, orbit needs to be transferred to a synchronous altitude. Or if it is a low Earth mission, means of course some minor orbit corrections needs to be done. So those things are all being coming under initial phase operations. Then comes on-orbit operations phase. That is, once all these initial phase operations are over, like the orbit is fully established and the spacecraft is fully tested for its functioning, and then before handing it over to the users, we will test all its aspects. Then the on-orbit phase operation starts. So that means the actual the spacecraft usage is coming. That is being, the satellite payload is being used by the users, whereas the satellite health upkeeping has to be done by us. That is what is being done by our control center. So that is that on-orbit phase, what we are calling it as. Then, of course, for everything, some end needs to be there. Okay, so the satellite cannot work indefinitely. Sometimes, yes, there could be some problems we will be getting into, or sometimes, yes, the planned life is over. Then we have to decommission the satellite to avoid the interferences from the other working satellites. Okay, that is the main thing. It is for the decommissioning. Why we? That means the satellite telemetry will be cut off. That is, no signal will be emitted from the spacecraft. So that is called end of life study as well as the decommissioning. That is, that end of life study gives what are all the, because after having spent crores of rupees, and we just can't leave the spacecraft. No, so when it is going to be in its life, useful life, where I am talking about, it's not that from orbit it is going to be deorbited or it is going to be entered into the atmospheric phase and then no. I am talking about the usage of the spacecraft by the users. And let us assume that if you take a communication spacecraft, the antennas needs to be always pointing towards the Earth so that the communication is happening. So for that you need to control the attitude. For controlling the attitude, you need the propulsion system. And the propulsion system, anyway, it cannot indefinitely work. It needs the amount of propellant what you have. So that propellant estimation and all we will do. That is how that end of study is coming to the picture. Then we are decommissioning. This is the typical mission cycle what we follow. Then what are all the mission elements involved? Okay. Yes, as I told you, launch segment. Once I decide my spacecraft, what are all the launch vehicles which are compatible to it, and what kind of orbit which I am going to take it. So from the available launchers, yes, I can choose. Okay. So this I am talking about in 80s. Now we have the options with us itself. We are having PSLV, GSLV, and then now LVM, and then anyway NGLV is going to come. So that way we ourselves are having, but in those days we were not having, only SLV and ASLV were there, and PSLV to some extent. For GEO we were not having. It has come a little later. So for that we need to have that launch, which is the launch we are going to have. Then what type of orbit for the spacecraft's payload design and to meet the objectives and all those things. Then comes the spacecraft, that is the space segments, that is the satellite design portion is going to come into the picture. Then comes mission operations. Then comes the tracking and then ground segment, whatever we are trying to have. Then most important thing is that data processing, because the spacecraft health, we are getting it from the data, whatever we are getting from the spacecraft. So that way, data processing is the main thing. There it is archival as well as display of data into a meaningful way to the subsystem engineers and other people and all, as they will be coming in this data processing part. Then of course, if there is no user, there is no point in launching a satellite. So user segment we are supposed to. So I just given you not a thing, just a glimpses of the mission elements I have given to you. There are different types of spacecraft missions, like remote sensing, communications, then scientific missions. And there are again operational missions and experimental missions. See, one thing which I can tell you, I just cannot have one type of instruments which is going to be used for control either in the launch vehicle or in the satellite. Directly we cannot put it. So we used to have some kind of an experimental spacecrafts. Like I can tell you, our INSAT 2A itself was an experimental one, and because it was the first time we have done after Apple project. Yes. Then what we did in 2B, yes, that has become semi-operational. Next 2C onwards, it is becoming fully operational. Then kind of orbits, of course, this LEO, GEO constellations and all these things. Already, you people would have already known all these things. Of course, in the spacecraft family-wise, if you look at it, it is communications and meteorology, then navigation and positioning, of course, then remote sensing, then scientific missions. So these are all the 4 broad categories the spacecrafts are being divided, and then the operations. Each type have its own way of operating things. Okay. Then the most important thing is mission control center. There, what we do is scheduling and executing the spacecraft operations, orbit and attitude determination, orbit maintenance, then payload programming. It's mainly for our remote sensing and other things it will be coming. Then routine health monitoring. Of course, the satellite's health always needs to be monitored, and then it has to be maintained. And all the subsystem specifications are to be met, like temperature and all other environmental things we need to have. Then spacecraft data archival and management. It is archival. Why I am trying to tell you is, little later date, if the satellite develops a problem, we will see that how, why and how that is happening. Then I can go back to the satellite data previously, how it was functioning and all those things. So for that, data archival is required. So that way, that data management is the most very important thing. Then detailed analysis for spacecraft performance monitoring. That is whether the satellite is being functioning in its intended positions. So that is where that is coming. Then coordination with network stations as well as data receiving stations, as well as user agencies. If you talk of geostationary satellite, initially it will be put in a geotransfer orbit. So the orbit will be of 10.5 hours, typically 10 hours duration. And the spacecraft will not be visible always to our ground station. Then we need to have the stations across the globe. So we used to coordinate, and then we used to take those network support, and then we used to get the data and then perform the operations. Okay. Once I go to geosynchronous orbit, then on the satellite will is available to you always. Whereas that is not the case with the low Earth satellites, because for low Earth satellites, depending upon the orbit altitude, the visibility period is 10 minutes to 15 minutes only. So, but if you want to have the entire segments to be available to you, then you need to have. So I think now what worldwide we have our own setting up of the network stations as well as in collaboration with other spacefaring nations. Like that, we are doing it. Similarly, our network station support also we give to other countries. So that's how it is being done. Then this is a typical control center. That is how it is being monitored, and each control, the subsystem fellows will be having the terminals, so they can have the data and all. The overall control is by the mission director, and then the data reception and other things, then analysis of the satellite health is done by the experts in the initial time. Later, it will be taken over by operations center like MCF, that is a master control facility at Hassan, as well as in Bhopal. We have set up one parallel control center in Bhopal also. Like that, for lower satellites and scientific satellites, we have in our Bangalore station itself. For our deep sea, but the deep network stations like interplanetary missions and all, yes, we have again in Bangalore, we set up 18-meter antenna and 32-meter antenna to track the satellites. Okay. Then this is a typical spacecraft control center, because what is happening, that satellites needs to be tracked and then it has to be commanded. So telemetry we have to receive, and then the tracking is required to know the orbit. Okay, like that kind of a function is being carried out from the spacecraft control center, because depending upon the type of the spacecraft, the control centers are being kept and designed. Then now we will come to the main topic of the day. Okay, after having tested so much in the ground from its inception stage till its launch, at every moment the satellite is being tested, and then it is being cleared by the experts committee. Then only the next step is going to be happening, and after complete satisfaction or a complete understanding of the problems are all being solved, then only the satellite is cleared for the launch. Okay? Yes, of course. Then there is a big question is asked. Once we do all these things, then how do we get into a problem? Okay? See, it's a natural question, I am doing so much carefully, every step it is being monitored by somebody else, and whatever that again it is being taken over and then reviewed by another higher committee. With all these things, yes, the spacecraft functioning is getting affected. Okay, why it is happening? Then I can call it as anomaly, because things which are not normal, okay, we used to call it as an anomaly. An anomaly is a deviation from the functioning or performance of a subsystem. Actually, it is supposed to perform something like this. The behavior of the subsystem is already, we know it is supposed to be in this mode only. If it is not following, then yes, we call it as anomaly. It could be the satellite anomalies, are it's actually a mission degrading events, because once we see a problem, then yes, of course, naturally the market value is coming down for that. Any product, if they are having a problem, yes, definitely the product value will come down. So that is what degrading one. They negatively impact on our operational spacecrafts. That is another problem, because if one spacecraft, if it is behaving like this, then what are all the already launched spacecrafts? So now I will be getting the doubt, That also it can come anytime. Okay, that kind of a thing will be coming. Then all satellites experiences anomalies of some kind during their operational life. It is not that a satellite is launched and it is working problem-free for its entire life. it is impossible. So, but the quantum of or the type of anomaly defines whether the spacecraft is surviving or the spacecraft can be made use, or is there any alternate way so that I can overcome the anomaly and make the spacecraft functioning. Okay. Then the ranging severity, whether it is a temporarily one, let us see, I can say that some subsystem, okay, due to its power consumption, the temperature will be go up. So what we do is to keep the temperature under control, its usage, the power level, and the kind of exposure it is having in the sun. All these things we will see and how to reduce it. So that kind of an exercise we will do it. Okay, that it's a temporary one. Whereas there are things which can be of rather disaster. That is, we can lose the spacecraft itself. So that is the kind of a thing happen. And of course, very rarely, we totally lost the spacecraft also. Okay, like what I can say, one of our satellite due to the power problem, yes, we have some completely without to give up the satellite. See, that those things are all very, very rare to happen, but yes, it okay, you will have to take it up. But then see next time what best you can do it so that the same problem is not recurrent. One thing which I can tell you, the problem which we faced in one spacecraft, I have never seen that problem getting repeated in the other satellites. So we will be thinking, yes, we have taken care of this problem. I think at least this satellite will be working problem free. When I be thinking like that, next moment there will be another problem which is totally different from what we have. So that is where all these things will be coming. That's why I was telling that. That's the reason I put that challenges and then how to mitigate it. Okay. Then anomalies can be categorized in two types. Anomalies in the initial phase itself. That's what I was telling you. When the satellite itself is being in the testing mode before giving it to the users. Okay. So whatever problem we face, yes, we used to resolve and try to understand and then make it pakka. So that is how it is. That is the subsystem as a problem from the starting itself. That means, okay, I can, whatever unluck thing which has happened for our NBS-02, it has started in the beginning itself, because there was a problem in the pyro valve, and of course, because of that, yes, the orbit could not be raised from GTO to GSO. So, in the beginning itself, the problem has started. Now, yes, our entire ISRO brain or the working and then finding out how to come out of the jigs. Okay, I think yes, the solution will be found very soon, and then we will be able to make use of the spacecraft to some extent. Okay, yeah, that is a different thing. Then next type is anomalies that develop subsequently. That is after initial phase of working during the on-orbit phase. Okay, the subsystem, it was functioning normally. It will be showing some kind of a degradation performance, or some things can fail. Some components can back off. Due to that, yes, something goes. So those kind of things. That's where the two categories of the anomalies are coming: the beginning or in the subsequent phase. Of course, why anomalies are coming? As I told you, it's not only the understanding of the spacecraft and then doing the testings and then reviewing the test results and then clearing it for further operations. All these things are being done. But in spite of all those things, there are few things which are not under our control. In the environment, once you launch the satellites, that is electrostatic discharge. It is the surface level itself, it can happen. There is an ion sputtering or atomic oxygen erosion. Then internally spacecraft itself, there could be an electrostatic discharge is happening. There could be some kind of a open thing or kind of a discharge. It is a very common one. Yes, of course. Then single event of absence. Then ionization loss that can be coming because of cosmic rays, trapped radiations, and then solar particles. This again gives me a kind of failure in the subsystems. Okay. Next one is radiation damage and degradation due to the Van Allen belts and then solar belts. Because these are all what is happening. We don't have a finite numbers and the period where it can come, because all these things are all random. Okay, like solar wind. Okay, I think all of you are aware of this solar flare. At least to some extent now we have once in 12 years that solar flare is happening, and then the peak activity is coming. The period. See, these are all what I can say is just a kind of yeah, it may come, or if it is not coming, you cannot question. But where at least which period it is appearing, we have. So what we do whenever there is a solar flare and its activity is very high, we used to switch off the high power mode systems so that we can keep the satellite safe. That is another way of looking at it, and then save the satellites getting into the anomaly, and then the satellite cannot be made use kind of it. Okay, it's a preventive measure what we can have. Okay, but because these things are not in our hands. Okay. Then comes the categories of whatever we can see. I think, are you able to see space charging due to the plasma environment? Okay, and then macroscopic particle environments, and then man-made debris. Of course, in the first man-made debris has entered into the spaces with the launch of Sputnik by Russia. Two pieces were, until then, space was fully free. With the first launch, two pieces was there. But as the day grows, okay, today we are having the millions, even the paint which is getting a flake which has come out of the spacecraft or somewhere, even it is as small as few millimeter by millimeter area. That particle, it travels with a speed of around 80 kilometers per second. So the impact which it can cause, though it is not having a mass, but the velocity, that creates a problem. So it can kill the working satellites. Why? ISS, we have seen the experiences, and to avoid that, they did the maneuver and then do it. Even during our launch, liftoff time, what we do is the trajectory path, we will see the debris which are present. If it is so thick, what we will do, we will delay the launch and then try to see how the debris management. So that is how we could delay the launch by to an extent of few minutes. We used to delay and then launch so that the lift off to the satellite or rocket, it is free from the debris. So that way, debris can create a very big problems. Then comes mechanical failures. Of course, mechanical things, which not only electrical things fail, mechanical things also do fail. So the solar panel rotation, then solar panel deployment itself. I think I can quote you one example. My first spacecraft happened where I joined. No, everything went smooth. when the deployment command was given, north panel didn't deploy. What do? We can't abandon the satellite. Then, of course, I will come back to that story a little later. Okay. Then we can have gyro failures. Gyros are used for attitude control, you all know. Then wheel failure for a momentum bias or momentum stabilized systems. Momentum wheels are used, or leaky thrusters. Of course, the thrusters, if the walls are not, the flow rate or the leaky rates are beyond the limit, before it is launched itself, it is tested, as I told you in the beginning itself. But due to so many other things, a small particle which is sitting in the seat, it can cause the problem. Okay, so that leaky thrusters also can be a problem, or there could be a software problem also in the logic. What I can say, if you recall our Chandrayaan 2, it was okay, attributed to the software failure. Then operations, of course, this is very, very rare due to wrong commands or the sequence in which it is being operated. Yes, sometimes some subsystems can behave in an anomalistic way. See, because the sequence of operations are being defined, you are supposed to do in that particular sequence only. If there is a change, or if that in that sequence, if one of the command or one of the function, if it is not being carried out on board, then it leads to further problem, and then we get into the satellite. Okay. Yes, I can tell you how the impact of one system failure from all other subsystems. Okay, so this example I have taken is our Apple spacecraft. So north panel didn't deploy. So half of the power generation has been already taken off. So you are having only 50% of the power generation. What do? First, we will do a Venn diagram. Because of this, what are all the subsystems which are being affected, and then how it is being getting affected. That's what I have tried to put it in a Venn diagram. That panel deployment. First, the affected person is power. Okay. Then next, thermal. Once power is not there, then thermal system, if there is a lower temperature, to heat it, you need the heater. To put the heater, I need the power. So that's all. From thermal again, orbit. That is how the orbit is. So that the power generation is being, we can have an estimate. Whether it is in eclipse or it is in sunlight, that kind of a thing. So that's how orbit is coming. Then attitude control. Accordingly, yes, if the working panel now, I should always try to pointing towards the sun so that I can have the power generation all the time whenever I'm in sunlight region. Okay, that is the thing. Then lastly, it is payload, because payload is the main thing for the satellite. If there is no payload, then there is no satellite. So what we do is, oh, okay, sorry. Okay, then that is a kind of a thing. Okay, I think this will give you how do we approach a problem when there is an anomaly that occurs in the satellite, how it is affecting, how to take care of all these things. Then how do we do the mitigation process? It could be what we are doing is to have the charging, that is that the total dosage and the internal chargings. This, by having a proper shielding there, we can avoid this problem. Then dischargings and chargings. This make the electric critical circuits insensitive to small spikes. because there could be the spikes happening, and that too can create this charge and discharge problems. Ground high impedance subsystems and protect the inputs. Then use shielded wirings, especially on exposed cables. Ground thermal blankets and use conductive or semiconductive materials. Test devices for susceptibility to the discharge. Then comes a single event upsets. At part level, maximize the critical charge required for an upset to the design, and the circuit level. Use onboard error detection and then auto correction methods. At system level, add filters to suppress the propagation of the fast transients so that we can avoid the single event upsets. Then comes mitigation based on the analysis. Some of the anomalies can be overcome by the following method. Use a redundant systems, but this is not possible always because weight and volume is the main constraint for me. So wherever possible, and without violating the mass and the volume constraints, yes, try to give a redundant systems so that you can switch over to the redundant systems. Then adapting recovery and contingency measures. That is like, okay, if the one panel is not getting deployed, how to take care of those things. Then mission operations to overcome the anomaly. Switching to a normal stabilized mode to some other stabilized mode. Like I can tell, if the battery is fully not functioning, then what I can do during eclipse period, the satellite cannot be maintained in 3-axis stabilized mode. But the satellite also has to be, can be used when it is come back to the sunlight. So what do? During the eclipse period, I used to spin the satellite and then leave it. So that satellite is being kept in a spin stabilized condition. Once it is coming out of eclipse, then the panels start generating the power. Then I will go back to 3-axis stabilization and then use the panel. So this is how, in fact, one of our satellites, yes, we did one of our INSAT 1 series satellite, we adopted this technique. Then, of course, sometimes we used to, our INSAT 2E, we had a peculiar problem. Persons are used to misbehave at times. At the time, what do? We used to map the VHRR images and then try to see the attitude errors and then control the attitude during those times. So there are, of course, without problems, our intelligence cannot be made use how to overcome. No? So that way, always you need the problems. Then only you can think and then you can work. But that does not mean that you have to design a satellite with a problem and all. Yes, I think if it is problem-free, finally, for the operation people, there is nothing, as well as for us also. Okay, that way, in one sense, yes, problems will be really required, but it should not be in the disastrous mode. That is where the point of interest what we should have is. Then mission control evolution. Finally, yes, this is my last slide. Then fault tolerant design, of course. To the extent possible, you have the fault tolerant. Then database of all the failures what we have encountered in the previous one, so that in case any anomaly happens, try to correlate with that and then see what best can be done, or is it a repeat of that problem, and how to overcome all those things. So that way, this database of all failures during the testing or as well as the on-orbit mode we used to have. Then deep learning and then analysis and then machine languages we can adopt. And then this mainly because the volume of data available is so much, it is very difficult for us to manually compile and then have all these things. So that's why these kind of techniques now it is available for us. So make use of those things. Then AI tools for autonomous operations. Yes, of course. We have adopted from our Chandrayaan stage itself Because when the Chandrayaan, when we launched, the deboost motor firing has to be done when the satellite is not visible to us or anybody else, because it was on the backside of the moon it is happening. So there, yes, of course, we will have to go for a autonomous operations. That is, it's a time-packed one, and then we used to trigger the train, and according to the sequence that time, it follows, and then yes, we have done it. So this is another very big use for us, and now for almost all other satellites, now we are adopting this technique. And then use of long short-term memory deep neural network, that LSTM. Of course, it's in the now nascent stage, and of course, people are trying to have something and then have it. I think because of the lack of time, I'm not able to. I thought I can give you a few examples, but I'm sorry. Before I could conclude, sky is not the limit for us. Nothing is impossible with hard work. Nothing is possible without hard work. We are better among the best. Thank you very much for your patience with me. I think some questions, or I don't know, I think the organizers have to tell me.
Good morning, sir. My question to you is that in 1965, some Russian hackers hacked into a satellite from US. So when we decommission a satellite, there are chances of hackers to hack that satellite and use it for themselves. So have we faced any kind of threats like that into ISRO or any kind of satellite which has been decommissioned by our own space programs?
See, one thing I can tell you, once the satellite is decommissioned, okay, to me, of course, because I'm into this for the past almost 40 years, because I joined in the ISRO itself in the mission group only. So to my knowledge, once a satellite is decommissioned, the satellite is put off, hacking is impossible. Okay, so that way, whatever that 65, that too in 65, anyway, I don't want to comment on anything on that, but one thing I'm sure, once the satellite is off, nothing you can get, that is where my point of view. So that kind of a question doesn't arise at all for our mission or anybody else.
Okay, sir. Thank you very much.
Okay.
Good morning, sir.
Yes.
My one question is like, at that time you didn't have that much technology. So how did you manufacture the ASLVs and all the challenges you face and overcome it to make that?
I think it is a question cannot be answered in such a short time. It is not that the ASLV or SLV has not come in a day or two. It almost took for us 6 to 7 years time, and thousands of engineers have put their brains behind it. Okay, and of course, see that's where our Aryabhatta, I can tell you. In fact, my people Aryabhatta, I was also not there, but I think in April they are going to celebrate 50th year of Aryabhatta launch. But that team used to tell me when the 70 odd people who were responsible for the Aryabhatta launch, they used to tell, we were not even seen what a satellite is, but we have been asked to make a satellite. See, that is the kind of an environment we were. But of course, with almost some references and other things are all available already. Prior to that, not many satellites have been launched. So you collect those data and then go through from the bits and pieces, whatever available, or whatever from our engineering degree, whatever we study, try to piece and put it together and then make it. This is how we have achieved. That's the main reason. If you look at it, all our first attempt, we landed in a failure. SLV.
Yes.
In 80 we had a failure. ASLV, yes, we had a failure. PSLV, we had a failure. And that's how, because first time when it is being assembled and then put on all these things, you really do not know whether you have done it rightly or wrongly, because there is nobody who is going to tell you, you do this, that and all. Because I only have to do it and I only have to inspect it, I only have to test it. That is the kind of a thing. I means, yes, we, our designers. So that is the kind of a thing. Okay. So it's not a, I can't answer in a few lines.
Sir, no, actually, it's like, how did you manufacture it? Like, right now, like, there are external manufacturers to produce.
No, why? Now only this external manufacturer and all, they have come only component wise. And 2 years back only, now they started even a fully private flow assembled a launch vehicle or a satellite is yet to happen. Okay, so it is a collective work of so many people and the time period. See, I can tell you, when I joined, our lead time for manufacturing a satellite was not less than 30 to 36 months. But now the turnaround time has come. In 6 months, we can make the satellite and then do it. See, time progresses. Probably, yes, maybe when you people are taking the helm of affairs, you may be doing it in a month. I don't know. Maybe techniques, better techniques will be available to you. Better testing tools will be available to you, so that you can make the satellite in a much faster way. Okay? Yeah.
Thank you, sir.
We'll take one last question, sir.
Okay, fine. Whatever you say, I'm.
Good morning, sir. My question was, you mentioned design analysis. Could you elaborate on the design principles, and also you mentioned the spin to recover technique.
Okay.
Could you elaborate?
Design analysis, now I started explaining, it will take a lot of time. Whereas this, what is happening, I can tell you, for a geostationary satellite, for its functioning, the antenna needs to be pointing towards the Earth. For that, we use a 3-axis stabilized system. That means all the 3 axes are controlled. Then only you will be able to point the antenna towards the Earth. What happened was, in this particular satellite, the battery functioning has been degraded so much. When there is an eclipse, I have to fully depend on the battery only. When the battery itself is degraded, I don't have the power. So, but without power, how do I keep the satellite live? Okay. So the best way what we thought was spin around one axis which is having the control axis, that pitch axis. So around that we used to spin and then leave it. So luckily in a geostationary spacecraft, the eclipse happens only around 45 days, around March and then around September. So those 2 times, the satellite was put under spin conditions, so that satellite health is not affected. But once it comes out of eclipse and the power, the sunlight is available, solar panel used to generate the power, and then I make use of the power and then go back to 3-axis stabilized mode. So rest of the days the payload were used. So this is how is another way of using the satellite in spite of having the anomaly. We were making use by this adopting this technique, but of course during that eclipse of that 90 days the satellite was not available to the users. That is all.
So in short, to conclude, your problem started when the eclipse was there. You started a spin.
No. It is not that. Because the battery functioning is degraded, in eclipse, I require only battery support. Battery is the only support which can give the power. Because that itself is not available. How do I survive? See that 45 days, the survival of the spacecraft. So that we thought, after deliberating all the possible options, we finally concluded this spin mode is the best one and the easy one.
Okay, thank you, sir.
Okay.
Thank you, sir. Now we would like to call our conference chair to felicitate Dr. T.K. Sundarmurthy.
Thank you.
Now, we will begin with our panel discussion for today on theme Future Propulsion System with our topic as Advancing Propulsion Next Gen Aero Engines to Space Thrusters. I would like to invite our panelist, Dr. Professor Ajoy Kumar Rai, Sri T.K. Sundarmurthy, Dr. Muniyappa Nair, Dr. Theophilus Eclides, Dr. A.M. Pradeep, with our moderator as Dr. Surisam.
सबको बोलना जिसको इन्होंने बोला पहन ले, ये भी बोला पहन ले, और चार कितने लोग हैं? पांच है ना, छह लोग हैं, तो वो हैंड एंड माइक बोलना पर एक्सचेंज कर ले।
ये भी सब दो लोग को
ये
सब
जिसको देना उसके लिए यूज कर ले, वरना बहुत नॉइज आता है। इनको लगा देना, जिसको भी दोगे लगा दो।
नोटपैड
ये कल से कोई भी नहीं अच्छा एक और माइक था ना जो उधर गया था, बोले क्या दो कॉलेज दो कॉलेज देने, वो कॉलेज वाला एक रख दो बस, और क्या हुआ, बाकी लोग एक्सचेंज कर लेंगे। एक रख दो, क्यूएन होगा इसमें, क्यूएन होगा होगा लॉरी इसमें क्यूएन होगा, फिर एक माइक रख On कर दो मैं
Two replaces, but
Okay, good morning, everyone. I didn't hear anything. Good morning, everyone. That's better. I would like to welcome you all to this panel discussion. So we have 5 eminent speakers, experts in their field. And the topic for this panel discussion is advancing propulsion, next generation aero engines to space thrusters. It's a very interesting topic. And the format that I propose to follow is what was followed yesterday for the panel discussion. So what I would request is, I'll request each of the panelists to speak for 5 minutes on this topic. And after that, we will open the floor for any discussions. And then finally, we will summarize the messages, the key messages from this panel discussion. Okay, so without further delay, and just before that, I want to check with Dr. Prashant. Dr. Prashant is it? Dr. Prashant. Dr. Prashant, there has been a delay in starting this panel discussion by about 40 minutes. So how do you want us to deal with this?
So 45 minutes it will go. I'm not changing anything, sir.
Okay.
The tea and refreshments are coming here itself, so that it will continue, sir.
Okay, so we go ahead with the same duration.
Yes,
Okay,
yes.
thank you very much. Okay, so our first speaker is Dr. Theoclis Nikolaidis.
Can you hear me? Okay. Thinking about the future propulsion systems, we need to think what is the drive for that? Why we need to change the technology? And obviously, with regards to the civil aviation there and working on the drive is the environmental impact of civil aviation. And aviation is facing many challenges towards this direction. So environmental impact now is a big challenge. In the past, we used to design engines with objective of efficiency, to optimize the efficiency. Nowadays, we discussed yesterday for sustainability. This is the key drive. So environmental impact and sustainability. So it seems that the current engines with hydrocarbons as fuels does not help to that. We produce emissions as we fly. And the projection is that the passengers will be not double, but probably 10 times more in the next 20 years. So in order to reduce, in order to reduce emissions and meet the targets of, as we call it, net CO2, zero CO2, then we need to talk about disruptive propulsion. But disruptive propulsion cannot happen in a weekend. So the scientific community, and particularly the operations of aviation, is talking about short-term solutions as well. So with short-term solutions, biofuels is something which actually is regarded nowadays. So biofuels, of course, the question is where you can find the biofuels. This is, yes, this is a challenge as well. But with regards to the airline and the aircraft operation, the biofuel is a short-term solution for that. It looks that it minimizes the emissions. And as we have discussed yesterday, it minimizes contrails as well. But this is the short-term solution. In the long-term solution, probably a disruptive fuel is, of course, hydrogen. With hydrogen, we have zero CO2 emissions, yes, but there are many challenges with regards to the aircraft. The aircraft design needs to be modified because we need to accommodate, particularly the fuel system has a there are many challenges with the fuel system of the aircraft because hydrogen is a cryogenic fuel. It is stored in the liquid phase, that means minus 250 Celsius, and then in the engine fuel ejector is at around 150 Celsius. So it is converted from liquid to gaseous. So there are many challenges in the fuel system of the aircraft. The aircraft should be modified. So this cannot happen in a weekend. It takes time. Apart from that, we talk about hydrogen not as a direct combustion, but a combination with fuel cells. So scientific community is looking to this solution as well to see how they can utilize fuel cells in combination with a gas turbine engine in order to support and provide the power to an aircraft. Again, this is not easy because in an aircraft, particularly the long-range aircraft, we need a huge amount of power. So these are things that we are looking as a potential solution for this challenge of the environmental impact of aviation. So it looks that the future is quite fascinating, and we will need a lot of resources in order to investigate and offer solutions to that. So I don't want to exceed my time. This is my
Thank you very much, Professor Nicolaitis. Our next panelist is Dr. Muniappan. So I'll request him to share his views.
Yeah, good morning, all. Like the future trends in the propulsion, right? So if you look at that propulsion, right, the propulsion is like, the Latin word starts from pro, is like, forward, and then is like, to drive. Okay, so that's the propulsion system. See, this it works in the, everybody knows that Newton's third law, every action is having an equal and opposite reaction. When you want to go into the propulsion system design, okay, when it comes to the aviation industry, this initially it was there for the marine applications, but when we come to this, the turboprop engine, turbo fan engine, and then right currently that CFM engine, whatever being working on this, right? Where and the air and all, right? What is the kind of, right, the energy or the thrust, or that you can say like, specific impulse is produced in the point of, to accelerate fast. Impulse is nothing but rate of momentum, right, within that given fuel quantity. For example, 1 kg of fuel, how much moment or is going to create for how long period of time. The same concept is applied even for that, in the rocket engine and also for the your aerospace aviation engine. So the currently what happened, right? We are as those told about, right? The future propulsion. You have to consider the the carbon emission and also the efficiency, right? And these are the key things we have to take into consideration. At the same time, when you're going for the future aviation, right, we are wanted to fly with the hypersonic and then supersonic speed, and then right, the kind of impulse it is going to create in the short time, and within that time, how fast it has to move, and your system has to work for that particular things. For example, currently whatever that turbo jet engines, whatever being available, we have to go for the ramjet, scramjet, the ramjet. So also you can accelerate more. It needs some initial velocity, unlike your jet engines. So we have to scramjet, and so many other propulsion. The development is already happening to meet the current or the future. The propulsion requirement to fly at high Mach speed. Okay, and in order to do that, another area like for the rocketry side, this Hall thrust sensor, that is all thrust that is also being used. There is nothing but your plasma rockets. It is worked based upon like electric magnetic field and electrical the field effect, wherein, right, it's kept in the axial direction, and your electrical field is kept in the axial, and magnetic field kept in the rotary direction. So these are like, different, the propulsion system which is tested in NASA for the rocketry propulsion. These are all the things which will be right for the future, which can be, the used in terms of lesser pollution and very effective, the giving the high specific impulse to the, there could be a space, and also for the aviation applications. And also, in adding to this, right, we need to consider, the AI and also your other technologies, data science or data mining things, to see that how to improve the efficiency of this engine. What is the kind of parameters, which condition this is very efficient to give that right higher mode of thrust. These are all the certain things you have to take into consideration in designing things. Yesterday we had two keynotes from the Airbus, and also one is from the Pratt & Whitney. We look at that, how they are working on it, like to improve the efficiency of these and reducing the carbon footprint by using SAF. Anyway, I will be having the session in the afternoon. I'll be talking more about the SAF, another area that is happening around the world to reduce that, right? Sustainable pollution by using the sustainable aviation. That we'll be talking. And next propulsion is interesting. One is electric propulsion, which is very, very, pollution free. But currently, we can go for that DEP, that is distributed electrical propulsion, wherein, right, instead of having one engine or the one motor, we'll have multiple, the motor installed in the span of the beam, right? That will be more efficient. For example, for the given propeller diameter and then motor capacity, it is going to give you the limited power only. If you keep that, that is completely constrained by your batteries. So when it's in the ground, we can have the, the required amount of power supply. When it is in the air, we need to depend on the battery. That's one of the challenges faced by the community in introducing the electrical propulsion, and also the other companies and the world already working on this solar-based electrical propulsion system. There is a company called Skidwheeler. It's a US-based company. Already they did a solar-based electric propulsion aircraft, and another company in German-based. They are also working on 80-seater electric propulsion-based aircraft. So these are all some of the the new propulsion system, which is very, very promising for that future need of the both aviation and also space applications. That's my view.
Thank you very much, Dr. Maniappan, for your sharing your insights. I will now request our next panelist, Dr. Sudhir Mistry, to say a few words on.
Because I'm being in mission operations all along, I can say something about the spacecrafts and our see the propulsion system now currently whatever we have in our rockets. Rather, what we have is, of course, solid as well as liquid and cryo. But now, anyway, semi-cryo is being attempted, and then we are on the way to adopt it. Of course, soon, once it is coming, the handling in the first stage itself, it will be much easier once semi-cryo is coming into the picture. So that is one area which I see there is a ample requirement, as well as the urgency is there. We'll have to somehow achieve it. That is one thing. And second one is, now we should have a efficient propulsion system. Currently, if you take, if I want to send a spacecraft to Mars, it almost takes close to 9 months. So what we are thinking of establishing a human habitat there, I think with this kind of a travel time, still it is, to me, rather, maybe there are a lot of others experts' opinion may be something, but what I feel is it is really very difficult for us until we cut down the travel time by having some mode of efficient mode of propulsion system, which is, of course, rather, currently I don't know what it is, but it has to come. And it will be coming because 50 years back we were not knowing even cryo and liquid. We were having only solid. No? So that way things gets evolved and then we will be having maybe. But the time frame we can't define. Maybe in the next decade, yes, someone would be coming out with some idea, yes, so that we can travel much faster than what currently we have. So that is one aspect. From the launch vehicle point of view, the propulsion system, yes, it has to be get evolved. And if we want to succeed in having a Mars colony, at least moon, it may not be a problem because in a day, you can have it and then, okay, going and coming may not be a very big issue. Whereas Mars, yes, until that day is come, to me, yes, it is the most crucial one, so that the advancement in the propulsion system should happen. Next thing is on the thrusters issue. Now, currently, whatever we are using the bipropellant thrusters, yes, that needs to be, yes, of course, with augmented electrical and all these things are all happening. Yes, yeah, full-fledged electrical thrusters should come. Like already ESA demonstrated that, and they have already sent a probe to moon a decade back. So we have to have, and of course we are already into it, and then a few of our satellites had a few number of thrusters on the electric propulsion. Yes, that needs to be evolved for all the control if it is been adopted. Now currently whatever the payload capacity what we are having in a 6-ton satellite, we can easily get it in 3+ ton itself. We can achieve that because in the 6-ton, more than 60% of the mass is the propellant. 60 to 70% is on the mass of the propellant, which is required for orbit transfer itself. And then another 20% required for the entire 20 years period of the life. So that can be cut down considerably so that your spacecraft mass can be brought down. Naturally, once the spacecraft mass is coming down, the launch vehicle capacity also you don't need that such a high capacity. So that way, the requirement on the launch vehicle also will come down parallelly. So that way, we can have a more efficient spacecraft bus as well as a long operational time. Now, with rather bipropellant system, we can talk of something like 10+ years or 15+ years with again that kind of rather availability of the propellant. Once this electric propulsion is made and it is fully available for our operation, the only thing is, yes, solar panel power generation, that should not be a very big deal. I can add 2-3 more wing so that I can easily get the power generation. That is not a big deal. Whereas the mass can be considerably bring it down so that our launch cost can be brought down. Satellite building cost can be brought down without compromising on the maximizing the payload and then its utility. Okay. So that way, I think beyond this, I don't think that I'll be able to think of from this side because this is basically not my bread. So that way, but these are all the two things which I thought, yes, it could be a necessity and it is what is supposed to be evolved. But of course, some things are already in the system available to some extent. We have proved, but it needs to be perfected, and then we'll have to adopt it into all our satellites. I think. Thank you.
Thank you very much, sir. Next panelist is Professor Roy. Sir, may I request you to say a few words on this topic?
Yeah, so thank you. A very good morning to all the participants. I mean, there are only a few observations from my end. Number one is the whole issue on sustainability. It depends on propulsion system. So obviously propulsion is the major thing in addition to the other issues for achieving sustainability. And I'm very happy that we have got a galaxy of true experts who have been working in these areas for such a long time. This is not my cup of tea. But I can tell you 2-3 things as my previous speakers and next speaker also will talk about. There is absolutely no alternative to going for full electric propulsion. So fully electric propulsion is a very, very far cry. Yesterday I was having a talk with Professor Pradeep. So he also agreed that it cannot be done not only overnight, it will take at least 20 years from today. You will be seeing it, but we may not see that. So that is one thing. Now comes, the hybrid. About SAF, Professor Muniappan will talk more about it in his next speech. But most importantly, there is a problem, there is an approach in systems theory, since aircraft and aerospace is a system, which says that if the complexity of the problem is very large, then you better convert it to a set of simpler problems. If the complexity of one system is large, go for parallelism and go for having multiple distributed systems. In fact, in computer science, we do the same thing. So here also, so far as the propulsion is concerned, Professor Muniappan also has pointed out to that. The best thing, in my opinion, I am not an expert, but then in my opinion will be to go for multiple number of systems which are, and that will also give a lot of redundancy, because more you have in your system multiple number of redundancy, that will add to redundancy. More redundancy means it becomes more safe, efficiency will be more, complexity will be less, and it will be achievable. All that you will need is some kind of a smart switching system. Now in this smart switching system, which now is one of the major problems. For example, even while giving power in our electrical systems, for example, now we have got solar, wind, the conventional fossil fuel-based power plants, and so many other things. So what do? You are using hybrid kind of multiple sources of energy, and then when one form of energy is not available, you just switch it to the other thing. So this is known as, even in our grid we do it. Constantly, the power system engineers, they do the smart grid is a very important concept. Here also, possibly the switching will be more important. So multiple number of redundant systems, smaller systems, electrical is absolutely the final goal. If we talk about the next generation, at least in the next 20 years, without that, there cannot be any kind of sustainability so far as aerospace and aeronautical sector is concerned. So for that, you need to, again and again I'm saying, you need to introduce a lot of mathematical modeling and a lot of systems engineering approach with mathematics to be understood by the students. That means which one, how much, and in fact, you might have noticed that during the last 36 hours of brilliant lectures by our professors and experts, they are all from this area. But one thing that has come while talking about, say, contrails yesterday, so a particular problem, why it happens, there may be several reasons. Now, mathematically, there are techniques which are available that you can decompose that, and you can very specifically say that which one is responsible to which extent. So similarly, even in power systems and in providing the power to the aircraft, to the, for example, he said a very nice thing that is, see, in spacecraft, solar is a very important thing. Now, what parallelly has to be done is to increase the efficiency of the solar cells and as a result, the solar panels. Currently, the solar cell efficiency is how much? Hardly do you know, 17%, 18%, 19%, 20%. If somebody comes up with 21 to 22% efficiency, that's a big efficiency. We have to enhance that. So there has to be a multidisciplinary approach from several areas and a systems approach with absolutely a complete mathematical model about power systems, about propulsion systems, just as in other areas of the structural aspect of the aircraft and aircraft carriers, etc. Thank you.
Thank you very much, sir, for your insightful views on this topic. Our next panelist is Professor Pradeep. I'll request Professor Pradeep to share his views on this topic.
Thank you, and good morning to all of you. Being the last speaker, I have the advantage of listening to my predecessors and just say that I agree with all of them, and that would be the end of it. But since I've been given a few minutes, I'll take this opportunity to share a few thoughts on this as well. So the topic of the panel is to look at future of propulsion from two perspectives. One is for aviation, and the other is for launch vehicles and launch systems. So I look at this problem, let's look at the aviation part first. While we have seen a lot of discussions happening on things that can be done in the near term, which could be to do with alternate fuels like hydrogen or SAF. And a lot of work is already happening on this. And this is primarily to take care of the thousands of aircraft and therefore the engines that come with them. They're already they're already in service. So you cannot just discard them and come up with a new technology. So, and these will have to continue to be functional for many years to come. So alternate fuels like hydrogen with tweaks to the current engines is something that will help us sail through the next few years. But the eventual objective is by 2050, if we can reach net zero using this, which I believe will happen. But if you look at disruptive technologies like what Professor Theo was mentioning, I think that's the key to really futuristic technologies for aviation as we see it. One of the possibilities, and something that a lot of students also ask me in my lectures, is how come after Concorde, which was there 40 years back, and till about 20-25 years back was in service, we've never had supersonic transport aviation. I really don't have an answer to that. Just that there were a lot of factors which led to Concorde not being functional. One of them being that it was not economical anymore, besides other aspects. So till such time that there is a strong business case, as they call it, for supersonic or beyond transport to be worthy of consideration, that may not be an option that people may look at it seriously, especially given the fact that just because you can save time on travel, which may have been something that was a strong business case 40 years back, you don't really have to travel. We've had two speakers who delivered their talks yesterday sitting several time zones, away from us. So you don't really have to travel all the time for, business purposes, so to say. So supersonic or hypersonic transport may happen, but that is something that will also have to deal with the fact that we are discussing sustainability as the major focus now. Whether designing a supersonic, hypersonic transport aircraft, keeping sustainability in mind will happen or not. I'm not sure if I have an answer to that now. Now, however, if efficient mode of transport is what we are looking at, then there are solutions to, or possible solutions that have been talked about. A lot of studies have also happened, including some of the studies that were done in early 2000s on looking at alternate configurations for an aircraft. The aircraft that we know as of now is what is termed as a tube and wing configuration, which has been around for a while, and it is sort of reached a level where it is optimal for the kind of configurations and routes that we fly now. To look at alternate modes or efficient modes of propulsion, like distributed propulsion, or even all electric that Professor Ray was mentioning, one may have to consider perhaps aircraft configurations which are drastically different from what we are aware of now. Like one of the concepts that they are tying up with the idea of blended wing. You may have seen images of this as conceptual studies, and concepts like this do seem to agree that there is a lot of scope in exploring alternate aircraft configurations. So as far as aviation is concerned, I think it depends upon what we really want. Is it faster transport, or is it an efficient net zero or sustainable transport mode? And there are options for both of this, and I think in the years to come we will see more and more of these being there out in the open. Now, when it comes to launch vehicles, I think the key to future launch vehicles, there are two aspects again. One would be reusable launch vehicles, which again a lot of companies, including SpaceX, etc., ISRO is also working on it. With a number of launches to increase exponentially in the years to come, we will definitely have to come up with methods of being able to reuse the launch vehicles that we are using. So that's going to be a key enabler to all these missions that are being planned, especially towards Moon or Mars or even deeper space. Reusable launch vehicles will hold the key to enabling these, to become reality. The other aspect would be with number of launches going to increase, we would also have to look at the fuel that we use and the environmental effect of these launches. Right now, it's not really a major concern, but with the number of launches being projected to increase, we will perhaps have to look at also the effect of the emissions that these launches will have on the environment. So perhaps that's something that will also be of interest in the years to come, to look at propellants which are perhaps less polluting than what they are currently. So these are my initial thoughts on this. Thank you.
Thank you very much, Professor Pradeep. I think having heard all the panelists speak, you would have gathered that a variety of suggestions were put forth, or a variety of views were put forth on the advancement of propulsion in aviation as well as in thrusters. I think the topics spread across sustainability, looking at alternative fuels, looking at reuse vehicles, and so on. I think something that is good which has emerged from this panel is that there is an agreement by all the panelists, or there's a convergence of view that sustainability is a key going forward in terms of advanced propulsion. I think that is a key message from this. And I would like to open the floor for now questions from the audience.
Yes, please. Good morning, sir. I would like to know what's your point of view on advancement of Hell effect thrusters in spacecraft altitude keeping and altitude control.
See, of course, for a short-term kind of a thing, yes, we can use it. But in the long term and the kind of the requirements which are now emerging from the complicated payloads and then its pointing requirements and all. If you look at from that point of view, I feel the kind of torque which it is going to be available and the kind of thing. Okay, I can use it for a short term and then this kind of for a long time. This may not be of rather great.
Sir, also if you consider operating systems like real-time operating system versus Linux, which do you find better?
I think that computer expert can tell something. For me, so long they gives me a system which is interpreting the data or whatever the data I require. If they give me, I'm satisfied. But I'm not expert to comment whether which is best kind of a thing.
Thank you, sir.
Yeah, others can. Yeah.
Yeah, you know, I mean, as students, you have to learn both. And it's very important. For example, without Linux, you cannot move even a single step ahead. But then RTOS, that is the real-time operating system, especially in some such these cases, is also extremely important because after all, everything has to be seen in real time. And when things are moving at a faster dynamics, so you have to. And please go through some courses on both RTOS and Linux. Computer science courses are a must.
Good morning, sir. So I'd like to ask the panel's opinion about rotating detonation combustion regimes.
I'm not getting the question.
Like rotating detonation propulsion regimes. Like, is it sustainable? What is your opinion?
So maybe I'll take a shot at it. So I think that's a very, I would say, futuristic concept. That's the very limited studies, even in India, which has been taken up very recently. They have sanctioned a couple of projects on RDEs. So because it's at its very primitive stage in terms of, at least in India, there have been studies in the West, in Russia, and so on. I don't think there is enough data out there to say whether to address the sustainability part. That's when these become, used like what we have in aviation engines and so on. That's when we start worrying about sustainability. Right now, they are just drawing up with the idea as a concept. It's not reached a stage where it can be deployed en masse, and then we start worrying about sustainability. So right now, I don't think sustainability is an issue. It's just the concept itself needs to be proven. And then we can worry about the sustainability.
Okay, thank you, sir. And I had a follow-up question regarding the blended wing design, etc. I believe there is a wing design called the oblique wing design. So what is your idea about that? Like, how is it? Is it good? Like, what needs to be done to reopen that chapter?
So blended wing is a very interesting concept, but there are again a lot of challenges in how this is going to evolve, because the tube and wing configuration has reached a point where it is, we all, when we think about an aircraft, we know this is how it is. So it's set in our mind what an aircraft should be. But blended wing is a very unique concept, it has its advantages, especially when you look at distributed propulsion, etc. It is amenable to distributed propulsion. And in that regard, there are parallel concepts too, like oblique wing design and so on. And like your previous question, these are all conceptual studies right now. For us to, so there are no bad concepts as of now. Each of them has its pros and cons. And it's only when you start looking at its detailed design and other aspects related to how it's going to evolve. And eventually, for example, one paper I was reading talks about why blended wing configuration would possibly have an issue, because you will have passengers sitting several meters apart, and when an aircraft is going to take the slightest of a bank angle, you can imagine what happens to people sitting on the sides. And the window seat it's going to be scary. You'll be moving up several meters up in the air and down. So that is something that is also to do with how the concept is good, but what happens to things like these when an aircraft is supposed to take some slightest of the maneuvers, it could be amplified because you are sitting several meters away from the center line. So, yeah.
Thank you, sir.
So the blended wing body is a very interesting concept. Just to add to what Professor Pradeep said, it's not just the technology part, there is also social factors involved in this. So there are social scientists, social aviation psychologists who are studying about how this will be perceived. And the reason I know this is that I participated in one of the evacuation trials for a blended wing body several years ago, almost about 20-25 years ago, as a student. So we had a blended wing concept at Cranfield, which was put through trials. So the problem is that we are used to sitting, facing forward. But in a blended wing body, as Professor Pradeep mentioned, you'll be sitting sideways. And you might be sitting in different rooms, kind of compartments, depending on how it is configured. So psychologically, is it acceptable to you? What is the public perception of this? Will people be able to use this? It is like saying that, are you in a position to fly in a pilotless aircraft? I'm not sure anybody from our generation would be willing to fly in a pilotless aircraft. Maybe your generation or beyond that, it might be a normal thing. So there are a lot of the other factors that have to be considered beyond the technical aspects.
Yeah, and the blended with body is a very nice concept. It helps a lot the propulsion system because distributed propulsion is ideal fuselage actually for distributed propulsion because the fan are embedded in the fuselage. So that means that the propulsive efficiency of the system is excellent, let's say. The problem is rely on the utilization of this, yeah, from the regards to the propulsion is very good.
I just want to mention one trivia in this connection is that when you fly, you see those illuminated strips. Or when you fly, you see those illuminated strips on the aisle. That was something which was recommended by Cranfield University, or studied at Cranfield University by a professor called, she was an aviation psychologist, Professor Helen Muir. And she had conducted many of these trials. And as an outcome of that, that was recommended to the aviation industry that they should have these strips for defining the escape routes. Okay, so there are a lot of other studies beyond the technical part. Any more questions? Yes, please. Yugandhar.
So I had doubt regarding the sustainable propulsion for rockets. So why don't we do air to space launches like X-15 program NASA used to do before?
No, the thing is, of course, this is conceptually yes, but I don't know why it is not being pursued further. There could be some basic design flaw itself, could be the reason, but I don't know. I don't think we are into this anymore.
So because when we see in factor of safety and efficiency,
So we can just launch a rocket in the air rather than starting from ground level from zero.
No, but how do we take it to that altitude?
So like as a Buran program, Russia you have
Yeah, see, no. If all these things are, yeah, conceptually or rather theoretically, I can have. Why, if you look at our air breathing engine itself, so why it has not come so handy? It is mainly because it is supposed to be operable at Mach 2. But the kind of Mach 2 which you are getting, you should get it within 10 kilometers or 15 kilometers only. Then only you will be having a sufficient amount of atmosphere oxygen be available. But in practical, it is not happening. It is very difficult to have. So that is where all these things are, yes, theoretically, this will give you a very optimal solution. When it comes to practically and make a hardware comparable to that, there it becomes a kind of a very big issue, how to make it. The best example could be this air breathing engine. See, how do you take it to that? But within that range, you should. But again, the range available for us is also very limited. It's not that I can go beyond 30 or even 30 also is not a rather good percentage of oxygen is available to you. Yes. So that is the message. These are all the things which could be, but I cannot, because a rocket designer may be able to comment more on that. But because I basically, know something on the propulsion, I am telling all these things.
Sir, because this is the concept for 7th generation fighters right now. The requirement is to go into the space, do the tactical operations in space and come back. So.
What I would suggest is that Dr. Prashant has already started indicating to me. So because I think we already overshot the time by 1 minute, that's what he said. So may I suggest that if you have any questions, the panel members will be available here. During lunchtime or any other time, you can contact them. And I do not want to summarize this session because this is not something that you can summarize very easily. It's an open topic. So I would encourage you to meet the panelists and speak to them. And with that, we will conclude this panel discussion. I would like to thank all the panel members for sharing their views, and I request the audience to convey our appreciation to the panelists. Thank you very much.
I request our panelists to please stay on the stage.
All of us. Because something or other will be
Now I request our conference chair to offer a token of appreciation to all the panelists.
Thank you very much.
So the camera here is just your recording the audio the video we
Now, we will have a small 10 minutes break. It's my request to all the dignitaries and the participants to be here just after 10 minutes.
for your pleasure or with you. Yeah, that's why I said that it's very possible that the future generation can have pilots or air taxis without pilots, without people. Yes. But there are other social factors, no insurances, who is responsible for these things. Yes. You can go on a pilot, driverless vehicle, but if you hurt somebody, who is responsible for that? Whether the company that manufactured it, the company that bought it, or the person who's sitting in that, or the company who's leasing it, or the app who's. So there are other factors that have to be considered. Yes. Beyond. It's been like this presentation. Thank you, sir.
I will request students to leave the auditorium and come back within 10 minutes. The refreshments are outside the auditorium. Please proceed.
Yes, sir. Sir, would you prefer to go to the podium for briefing these matters? Unless others want to go to the podium. I'll set my presentation. I'll just check whether the presentation. Yes, sir.
What is the GSM of this? Last 4 minutes. Comes from it. Okay, so the question is action is there. Introduction to composition
रिमोट का है
Thrusters also there. Thrusters small length and thrusters. More than that. And they are also not very it, I believe you are right? It's got to see all of your current process. Anyway, you have to how to store that, how to anyway, even more research, tell us, series and research, what you have to do, why are you what you have to understand the basic fundamentals of it, understand more of it, why charging for example, Assault rate is like, for example, I need a, suppose I have a electrical motor, which is, they have electrical motor, I need to have a motor which is a program. So when we can power cable to the motor, generate much or that's the cost. Okay, then the motor is grams, 1 grams, 1000 amps, will be very high. That much has to be such. That has to be such much. Please have a battery. You have a battery. Battery catches. It's a 12 volt, 5 volt, right? It's always a 1 amps, 0.5 amps current. So power. Yes, yes, particular power. Being to I was one from the comes to a running device. So all these things are connected. When I look at resort is not sufficient. Don't build but won't even take up. You have to already currently have a much terms of top. Now I am to be get a point. So can Google be the employers say like current system Yuzvendra, please take your members there, please settle down.
Welcome back, everyone. Now, moving forward, Dr. Suresh Sampath, Professor and Head of Gas Turbine Systems and Engineering Operations Group at Center for Propulsion and Thermal Power Engineering, Cranfield, UK, has been instrumental in organizing this conference. He completed his PhD in fault diagnostic for marine gas turbines at Cranfield University. Sir also holds an MSc in Scientific Application Software and a BTech in Mechanical Engineering from GMU, New Delhi. He has 22 years of service in Indian Navy. He brings extensive expertise in gas turbines, propulsion systems, maintenance, and research and development. Now we request Dr. Suresh Sampath to deliver his keynote lecture on green aviation, sustainability, environment, and economy.
Okay.
Good morning, everyone. And can you hear me at the area? Can you hear me? Yeah. Firstly, I want to apologize that my throat is bad. So in case it comes out, you have to forgive me. I'll try as much as possible to try to keep it moist by sipping some water. I would like to thank the organizers for giving this opportunity for speaking here among this wonderful audience. And the panel discussion also has helped me in a way that because there was a convergence of view that sustainability is the key, and that's the topic that I'm going to speak on. So my topic for presentation is green aviation, sustainability, challenges, and opportunities. Before that, I will just briefly give you a glimpse of Cranfield University for those of you who have not heard about it or have heard about it and don't know much about it. Cranfield University was set up in 1946, and prior to that, it was Royal Air Force base. And you can see from the picture that we have an airfield, and it is the only university in Europe or outside the US which has its own airfield. It has its own flying school. It has its own ATC. So in a way, aviation is something which is part of our DNA, and it is what Cranfield is known for. So in terms of students, we are quite a small university compared to VIT. I think the student numbers here is in excess of 14,000. That's what I've been told. So if you say that we have 2,000 students across 2 campuses, and all these students are postgraduate students, we also have a large number of research students. So every student that you see at Cranfield would be doing their masters or they'll be a research student. And we also run a lot of continuing professional development programs. what they're also popularly called as the executive development programs. You see that the throughput is 50,000 and more. This is the hello from our Cranfield team, and you can see the Cranfield Boeing 737 with the Cranfield library on that. And originally it belonged to the British Airways, which is a BA flight which was decommissioned and sent to Cranfield for study purpose. In addition to that, on the top left corner, you see a Saab A340 aircraft, which is part of the National Flying Laboratory Center. And it is a flying classroom. So I'll come to that later. And the picture on the bottom right is part of our Digital Aviation Research Center. And you see that the plane 737 is parked in what we call as the hangar of the future. So it has various features, and it's beyond my presentation. So I can speak to you separately about this. And this is how the flying classroom looks like. And it is a 24-seater plane. And you will notice that the displays behind the seats are not for watching movies or web series. They are actually for serious business, for capturing data. And the professor actually sits here in the jump seat that you see, where normally the aircrew sits. So the professor sits there, and the professor is constantly in communication with the pilot. And these are not flown by students, just to clarify. They are flown by test pilots. And the students sit behind, and they have a briefing before they see Cranfield Airport. We have our own airport. So the briefing is given to the students. And after that, they go through the normal procedures. The boarding passes their university ID card. So they are boarded on the aircraft, and then it takes off from our runway. And usually these classes have two such sorties. I think each lasts about 45 minutes to 1 hour. And this facility is also used by 23 different universities for experience, so sharing for the students to experience what exactly happens for various purposes, flight dynamics, how the aircraft stalls, and many other things can be done with these aircraft. We also pride ourselves on having live test facilities. So many of these facilities that you see are actually industrial scale facilities. So you see the compressor testing rig and the combustion rig. All these are live industrial test facilities, and often these are used for testing industrial projects or research projects. So where our postgraduate students and researchers work on. Okay, so that was a brief overview about Cranfield. Now coming to the main topic of this discussion, which is sustainability in aviation. Sustainability is something which is very loosely used these days. Everybody talks about sustainability. I'm sure that you come across this word every day. I was traveling on the motorway back home, and I was telling my wife that whenever you see a word sustainability appear anywhere, just click a picture. And when I try to analyze the information, you find that almost everything would have this in some form. You'll find that somewhere it will say sustainably manufactured. Even the delivery ones like Amazon, they will say sustainably delivered, sustainably packaged. So it is a word which is very widely used. But in the context of aviation, what does it mean? So, in my opinion, sustainability is a very, very important word, and it has to be used very responsibly. With responsibility, in terms of aviation is a very high growth sector, and it is now that we are coming out of the downturn from COVID. Many of the airlines are now started smiling because they're back to their capacities now. But we all know what happened with COVID when aviation was suspended. It affected us socially, it affected us economically. Because aviation, and incidentally in terms of carbon, production of carbon, aviation contributes only between 2 to 3% of the global CO2 production. And yet, why is that the aviation industry has taken it upon themselves to go ahead and declare that by 2050 we would like to be net zero? Because it is an important industry, but you also need to understand that how many people fly. In a country like India with 1.5 billion people, the number of people who actually fly would probably be about 1%, 1% or 2%. A large part of the population still uses different forms of transport. Railway is the main transport. So there is a huge potential for aviation growth in India and also in many of the large countries, particularly in South Asia, the large population. So in terms of that, some of these figures that you see, the passenger flow, 4.5 million, and these may be a bit dated. Yesterday, Frank showed some updated figure. And if you see in terms of the GDP contributed by aviation, it's about 3.5 trillion, which is huge. It's much bigger than the GDPs of many countries. It also produces a lot of jobs, directly and induced jobs, not within the aviation alone, but through its supply chain and through many other channels. What we call as the induced jobs. So jobs for everyone, not necessarily for aeronautical engineers or aerospace engineers, for civil engineers, for computer engineers, for management, you name it, and you can find them in some way associated with this industry. It is also a research and technology intensive sector, and we call it as a donor technology because many of the technologies that are developed in aviation, it sort of percolates into other forms of other sectors. And it has huge socioeconomic benefits. And in terms of investment, the spillover benefits of aviation, when you make an investment of $1, it creates wealth of almost $30. So that is the kind of high growth sector it is. And therefore, when we talk about sustainability, the two important aspects that we need to consider is one is the protection of the environment, and the second thing is how do we drive growth? So when we talk in this context, sustainability is economy, environment plus economy, and we need to have a balance between these two. And in terms of the number of commercial aircraft market, you can see that by 2032, it goes to about $194 billion. So that is, and you can see that it is almost has an exponential growth. More than about 30,000 aircrafts are on order, which are replacement as well as new. Okay, I just want to give you an overview of the technology landscape. In terms of sustainability, if we have declared a date that is 2050 to go net zero, in the current technology landscape, how do we achieve this? So in our opinion, we believe that this can happen in 3 different phases. The first phase is called as the technology squeeze phase. I'll come to each of them later. And the second phase is what is we call as the transition phase. And the third phase would be the implementation phase. Now, what is the technology squeeze phase? Yesterday, many of the speakers, they mentioned about extracting further efficiency from the existing technology. So the first phase will involve, we have probably reached a point where you touch the plateau that even extracting or improving the efficiency by 0.5% would take tremendous amount of effort compared to the yesteryears. So during the technology phase, it's a very research intensive phase. It's a very resource intensive phase because what we're trying to do is to squeeze the best possible efficiency out of the existing components. Whether it is the components or whether it is the engines or whether it is the allied technologies which support this. In addition to that, there will be a transition phase where we talk about new technologies like sustainable aviation fuel, hydrogen. We're talking about electric propulsions or turboelectric propulsions, hybrid propulsions, or to the extent of nuclear as well. I will discuss about these things in detail.
Something which is very important is the implementation phase. While technologically we can achieve many of these things, that is the easier part. The first two part are the easier part. The third part is the implementation part. If you look at the implementation part, we need to consider a host of aspects in this. I put some of them in orange and some of them in pink. First is the technology maturity, whether the technology is mature for implementation, for commercialization. Now, who decides that? That will be decided by the industry and the certification agencies. Then you have the operations. Do we have the capability to execute the operation with the new technologies? Are the airports geared up for this? Are the pilots geared up for this? Or the whole infrastructure geared up for this? Then you have the social factors that we discussed in the morning. Are the people willing to this? What is the perception of the people? You need to develop the public perception. With the new technologies, would they be, for example, the blended wing body? Would people be comfortable in traveling with this kind of aircraft? There's a question of scaling up. It's very good to develop. It's probably easier to develop an aircraft which is flies with hydrogen, but are we in a position to scale up these things? Now, how do we scale up when already 30,000 aeroplanes are on order? You can't change overnight. Somebody said that, my colleague said that you can't do it over a weekend. It takes time. And in aviation, when you look at the transition phase, it lasts between 20 to 30 years for you to completely change over. Then what about the government policies? How does the government support? How does the industry get up to these things? When I say government policies, the regulators, the aviation regulators, how will they support these things? So the government, there needs to be a policy change. So the governments have to pitch in. So this will be the most difficult part in achieving this. Now, in terms of technology space, what are the things that we have been doing there? We have been looking at low fan speed. Yesterday, I think Sami mentioned about the get turbo fan. So high speed, I will not go into details of each of them. Slim and massive designs. We are looking at low NOx combustions. How can we improve the efficiency of the combustion system to reduce the NOx? We have been looking at variable pitch fan design, so that while landing, instead of using the thrust reversers, you can use the variable pitch fans. We have been looking at heat management. We've been looking at noise management, materials and weight. Materials will play a very important role because as we advance these technologies, whether in terms of you want to increase the cycle temperature of an engine, you need to have special materials for that. Special materials, coatings, manufacturing methods. So the concepts like turbine, barrier coatings, thermal barrier coatings, or environmental barrier coatings, many of these things. And I've also mentioned about the ultrafan, and Dr. Kishore is here. He has been working on the Rolls-Royce ultrafan project, and this is something a new generation engine in terms of how we can extract the technologies. More sustainable solution as a transition phase, more electric aircraft. So the Boeing's Dreamliner is called as a more electric aircraft. And why is it a more electric aircraft? Because a lot of components, like for example the actuators, which otherwise use hydraulics, many of the systems have been converted to electric because it's far more manageable and lighter. Then you have the hydroelectric propulsion, where we talked about the concept of partly having an engine and partly using a battery or any other form. Different concepts, not necessarily commercial fuel and electric, but different forms of hybridization. Turboelectric propulsion. This is something which has been spoken about. Why do we need the turboelectric propulsion or the distributed propulsion? Because as you want to improve the propulsive efficiency of the aircraft, you need to have larger bypass ratio, which means you need to have very big engines. When you have very big engines, you will have large drives. It increases the weight, and also it reduces the ground clearance. So it lays short. So the best way to deal with this is that you distribute these fans. So have smaller fans, but the power for this is generated through a conventional engine. So that's where the KDP concept comes. Then you have full electric propulsion. Full electric propulsion can be done in two ways. One is the battery. Now, battery has its own problem because currently the most power dense battery is considered with the Tesla battery, which is I think 224 kilowatts per kg or something like that. But if you want to have something worthwhile flying, then you need to increase it by at least 5 to 6 times, or at least 1,000 kilowatts per kg you need to have to make it more meaningful for flying. But battery comes with its own problem because if you increase the size of battery, the weight of the aircraft will increase. If the weight of the aircraft increases, the flying efficiency will reduce. You need more power to fly. So you will get into this kind of a spiral. It's a never-ending spiral. When the aircraft flies, you consume fuel, so it gets lighter, so it flies more efficiently. But if you have batteries, the weight doesn't change. So you need to have stronger landing gears. If you want to have stronger landing gears, then you need to have, they make the aircraft even heavier, which requires more power. And you can see that it sort of goes into this spiral. Then you have sustainable aviation fuel, which is a drop-in fuel. Most of the airlines prefer this because it does not require any change in the combustion system, and it is a drop-in fuel. So it has similar characteristics as jet fuel. So if you simply start using it, you're okay. And then we've been looking at blending these things, and the hope is that we will be able to take it to 50% blend. Then hydrogen. Hydrogen is used in two forms. One is the fuel cell form, and the second one is the direct combustion form. I'll talk about this in a little bit more detail. And the last one is nuclear. I said nuclear. I'm not expecting that the aircraft will fly with the nuclear reactors on board because it has got a lot of other issues, safety issues, political issues. So we will not talk about it. I've mentioned nuclear because nuclear will be, if you're going in for electric propulsion or battery propulsion, you require enormous amount of power. So nuclear could be a possible solution for producing enormous amount of power, apart from the renewables. And this is something which is a proven technology. Okay. Now, I will, out of all the sustainable technologies I've shown, I'll specifically pick out the hydrogen because we have invested a lot of time and effort at Hanfield in hydrogen propulsion. So if you look at this chart on top, it has various lines. It talks about departures, get departures from the aircraft. It talks about landing takeoff, knots, production. It talks about revenue passenger kilometers. Every airline defines its profitability or efficiency by the revenue passenger kilometer. The larger the RPK, the more profitable, the more money they can earn. Without going into details of that, if you see these bubbles, what we have evaluated is that if you see this little bubble, this is where the electric aircraft or the hybrid aircraft will fit in. And if you want to have meaningful long distance travel, we believe that hydrogen would be a key solution to this in terms of sustainability. Hydrogen has various advantages. One is that it's a power dense fuel. If you look at the calorific value of hydrogen, it is thrice that of the kerosene that is used. But the challenge is that it also occupies thrice the volume of jet fuel. The other challenge is that you cannot use it in gaseous form if it is an aircraft because you need really large volume. You don't want an aircraft full of hydrogen with just the pilot flying it and no cargo or no passenger. It is not sustainable. It also has got other good combustion properties in terms of lean burn, but it also comes with a lot of challenges because hydrogen has to be liquefied to be carried on board an aircraft. And if you want to liquefy it, you need to maintain temperature at 20 Kelvin. Storage of, it has to be stored at slightly higher pressure, which means that it will require a lot of insulation. A student of mine calculated the insulation for a similar application for ship. And when we're storing at a pressure of 1.25 bar, the insulation, thermal insulation of the tank required is about 1 meter, 1.2 meters thickness. So it is not feasible when you have these kind of requirements. It also has problem in handling hydrogen, safety issues, because hydrogen embrittles the systems and they would crack very easily. So you need to look at materials. Okay.
So we have done a lot of evaluation through our research camp project called Enable H2. And a lot of studies have been done, and we have developed a new form of low NOx emission combustor, which is called as a micromix combustor. And you can see the picture of this here. And this is being tried out in small segments, but what we're trying to do it is to convert this into a full combustor and test it with an actual engine. We have had this discussion during lunches and dinners about the effectiveness or comparison of SAF and hydrogen. I just want to give you a small comparison. So if you look at this dark brown patch, that is the CO2 emitted as part of manufacturing. And if you look at the touch portion, that is the emission during its combustion. So for a conventional jet fuel, this is the CO2 produced per megajoules of burning the fuel, combusting the fuel. And let's say this is in terms of SAF. The advocates of SAF, what they say is that we are trying to keep it net zero because they burn carbon, they combust SAF and we produce carbon dioxide, but equally we are also absorbing CO2 to produce SAF. Now, if you look at this, this is for producing SAF, and this is what is emitted by SAF, but there is a drawdown because you are absorbing the CO2 back from the atmosphere. Okay. Therefore, it is a neutral. In terms of hydrogen, there is a cost. You are producing CO2 when you are actually manufacturing, when you are producing hydrogen. But if you slightly look at it in a different way, in our perspective, this technology which you are using for capturing carbon dioxide, which is called as carbon capture methods, that you could apply even to hydrogen when you're using hydrogen. So if you actually use hydrogen and you apply this technology where you are able to capture carbon and sequester it, or you can put it to a different use, you would not take carbon neutral, but you could actually go negative. You'll be extracting carbon dioxide from the atmosphere. This is a point of view. We believe that any technology, the success of the technology depends on how the industry perceives it and how industry accepts it. If there is no route to commercialization, and if that technology is not going to earn you money, that technology would rather remain as a more of an academic study than of anything helpful to the society. It has to have a commercial benefit, it has to be sustainable, it has to make economic sense. So we believe that the implementation of hydrogen can be undertaken in 3 different ways. The first way, the most important thing is to bring it into service, the hydrogen aircraft. Now, what is required? So the first innovation will last 10 to 15 years, where what we are suggesting is that we should be able to use the existing resource. Use the existing aircraft, make minor modifications, and focus on certification. Because certification of an aircraft for flying, or an engine or an aircraft for flying, is a long drawn process. Because you have to satisfy the regulators and the certification agencies that it is safe for flying. Okay. So the first phase will involve focusing on certification. The second phase will involve, once we have brought it into service, then we know that this technology works very well and it is acceptable. Then we will focus on the second wave, which is the efficiency. So we'll try and improve the efficiency of this. And if you look at this, these are the kind of concepts that we're looking at, where you find that the hydrogen will be stored here, and also the other forms of like distributed propulsion, so hybrid propulsion. So that we expect to take about 20 years to improve the efficiency of this. Then you have the innovation where we talk about the fuel cell, where we can use fuel cells. And the last one, the third innovation would be where we'll be going for cryogenics, because it is still far away from implementation, the cryogenic concept for aviation. And then you look at the concept that we have spoken this morning on blended wing bodies. So maybe the future aircrafts
would look something like this. So in terms of entry into service, what we are trying to do is this is an artist impression. We have done some studies using our in-house tools for engine as well as for aircraft. So this aircraft that you see has 3 variants that we have studied. On the top, this is called hydrogen, very large vehicle, medium range, which will carry 388 passengers, and which will have a range of 3,300 nautical miles. And this is how it will be. This is the conventional aircraft, and the hydrogen tanks will be placed on the top. And for the purpose of studies, we have considered an Airbus 380, which has basically 2 levels. An Airbus 380 with an Airbus 350 wings and an XWB engine. So that is the combination that we have studied. The second one is the long range, which can fly up to 4,800 nautical miles. And naturally, it can reduce passenger capacity. The third one, which is the extended range, would fly 5,500 nautical miles. Now, why 5,500? Why not 5,000? Why not 6,000 or 7,000? The 5,500 is a magic number because if you want to fly from any place to any place on the globe, with one stop you can fly. If your aircraft has a range of 5,500, with one stop you can fly from any place to any place on the globe. And that's why we have chosen this as a 5,500 nautical miles. Okay, so some data that I have given. I will not go to the details of this, but it gives the various, this presentation can be shared if you want. This gives the various parameters for the aircraft. So how can we further improve the efficiency of this hydrogen aircraft? One point which is very important is the gravimetric ratio. The gravimetric ratio is the ratio of the fuel that is carried over the total weight of the fuel and the tank. Currently, these evaluations have been done with a gravimetric ratio of 0.33. We believe that as technology improves, the gravimetric ratio will also improve. And if we consider going up to a gravimetric ratio of 0.667, we could achieve a lot more through this. And how would this improve gravimetry? Basically, the improvement in materials. Whether you could have composite tanks or any other form of tanks. Currently, you're using aluminum, we are using steel tanks with foam insulation. Okay, so we also propose that for the hydrogen combustion to be tried, we propose that one aircraft that is suitable in real terms. The other one was more of a study. In real terms, we believe that the Hercules C-130 could be an ideal vehicle for testing a hydrogen engine, where the remaining engines could be the conventional engines, and one of the engines could be a hydrogen engine. And this is a concept which we have put forth, and this will be the trial vehicle. And I think Airbus has announced that the 380, one of the 380s is going to be a trial aircraft for this. Apart from in terms of sustainability, going forward, we also need to look at it in a holistic manner. So it is not just about the aircraft flying with hydrogen, but we are also creating the entire ecosystem for hydrogen. So you need to have hydrogen production, hydrogen transportation, safe handling of hydrogen, refueling of hydrogen as it is required. Not all airports may have the same facility. So we need to look at it in a very, very holistic manner. So our strategy for market entry, based on some studies, what we believe is that a hub and spoke model would be most appropriate for this. So if you look at these are 2 hubs. So the hydrogen aircraft would fly between the hubs because it will be a long-range aircraft. Whereas the spokes will be the intercity, city pairs, short-distance city pairs. They would be flown by, let's say, fuel cell.
aircraft powered by fuel cells or hybrid aircraft. So this makes more economic sense. We also done some route planning. So this is London, and this is the city pairs that we have established. And we believe that by having this hub and spoke model, the tankering will be much easier. So the strategy that we propose is that naturally all aircraft cannot be converted into hydrogen aircraft overnight. So what we have proposed is that we could start with 200. So 200, the two tankering hubs will be London, and here you all must have heard about the new city called Neom in Saudi Arabia. So Neom is the green city, or green sustainable city, a city of the future. So we chose this, not that we have special affinity to do this, but we have chosen this because hydrogen is likely to be available in large quantities based on the mission. So we believe that the first 200 could be run in this city pairs. Then we would expand the hydrogen hubs further down to introduce 400 more aircraft in service. And then with the passage of time, then another 1,000, and then you see that the hydrogen hubs will expand. And in India, we have chosen Mumbai as a possible hydrogen tankering hub. It could be Mumbai or any of these regions. It could be anywhere else. Okay, this is our proposed strategy for market entry. And just as a disclaimer that all these are academic exercises which we are evaluated based on our evaluation using our tools, but we will socialize these ideas with industry going forward. Okay, so integrating all these things, if you're looking at sustainable future in terms of aviation, we need to integrate this. So wind energy, solar energy, production of hydrogen, and you see the cycle, including all forms of energy production facilities that we have. So this is something that needs to be considered. Now, you should know that transition is always expensive. Any form of transition is going to be very, very expensive. For a country like the UK, if you want to go in for fully electric, the power requirement is about 4 times what it is now. That's the kind of power requirement. That will lay a huge stress on the existing infrastructure. But the reality is that it has been done twice before in history. If you look at this picture, between 1925 and 1940, in a gap of 15 years, the power production was increased by 4 times. The second time which was done was around 1950 to 1965, where again the power production was increased by 4 times. So it is possible that in the next 10 to 15 years, the power production can be further increased. Of course, we have a challenge now is that in those days, climate change was not such a challenge for everyone. But now we need to keep this in mind, so that is going to add to the existing challenges. And in terms of price, if you look at this is the price of solar modules way back in, I can't read it properly, but I think it's almost about 40, 50. If you look at this, the price was here, and today's price, there has been a drop in price of about 99% in solar panel. So as the technology improves, prices will come down, and these will become easier to implement. Okay, so we need about 15 years. I'm talking about the UK context because the study was done. So 15 years needed, and the money that needs to be spent is about 2% of the GDP, which is quite a lot of money. And plus, thousands of talented engineers like you will be required. So this is a very famous statement about gas turbine. Post-World War, when the gas turbine engines were considered to be introduced in aviation, they set up a high-level committee of very eminent physicists, engineers in Europe, and they wanted them to evaluate the gas turbine technology and advise if it is feasible to fly with this. And this was the statement given them. And incidentally, the people who were there were very eminent people, like the committee on carbon. Okay. And it was said that in the current technology, this could hardly be considered feasible application for flying. And you know today that
the gas turbines were the de facto power plant for flying. Therefore, what I would like to, the message here is that let's not judge the future with today's knowledge, because we don't know how technology will change going forward. Okay, so I think I should have completed half an hour in my own. So there is a homework for you now, for all the students. So the homework for you is that you need to share the socio-economic benefits of aviation. Okay, and you also need to convince that there is going to be a cost of transition which is going to be higher. Okay, so this is, and then you also, the success of this also depends on talented individuals to deliver the research analysis towards sustainable future. So you need to encourage more people to take up this role. And what is your reward going to be for this? So you're going to have a clean environment, exciting careers, you can travel, you can drive business growth, you can impact, you can have societal impact. There's a whole lot of things. Okay, will you do this? I didn't hear. Yes. That's good. Okay, so I would like to end this talk by saying that the future of decarbonization and sustainability is very challenging, but it's equally exciting and optimistic. So let's join to create a sustainable future at a time of great change. Thank you very much.
Yeah, Professor Suresh's nice presentation. Mainly, I know more about this hydrogen, fuel system now. So, what is the right? If you come to the hydrogen, it's very difficult to produce, and also safety consideration. What kind of safety consideration you taken into account in your complete study of the design of the hydrogen?
While doing this study, we are conscious that safety is an important aspect. But this was more about the performance of the hydrogen as such, because the safety is something which somebody else is studying. It's a huge topic. So what we've done is we're trying to do the analysis around hydrogen, assuming that it is available to us on board.
What is that, right? You're given that study, right? How you are comparing this, the fuel efficiency and the weight ratio in compared with your aviation fuel?
So the aviation fuel, the calorific value is about 43 megajoules. And this is about 120 megajoules. So the energy density of hydrogen is 3 times more than the aviation fuel. But the problem is that hydrogen is a very light gas. It's a monatomic gas, and it's a very light gas. So therefore, you need a much higher volume to hold it. So the issue is not about the energy density, the issue is about the volume of hydrogen.
Yeah, how are you going to store that? That's what my question is. I put it this way: since it's a low density, it occupies the very high volume, right? Aviation fuel is 750 kg per metric ton. When it comes to this, it will be very light, but though it's 3 times energy efficient, how the volumetric distribution or that the real estate of this is considered in your study when you take it into account.
See the aircraft that I showed, considerable amount of volume is occupied by the tanks. So that's why you have to shave off the passenger numbers. So in an Airbus 380, which takes almost about 600 to 800, depending on the class configuration, you reduce it to 332 in the medium range. Yeah. So because the tanks will occupy most of the volume. The tanks and insulation for the tanks.
So by that also it is you think it's beneficial to take out that seats to accommodate this tank?
At the moment we don't have a choice. We have to take out the seats unless we go for it. Because if you go for bigger aircraft, the airports will not be able to, because even A380 cannot be accommodated by all airports in the world. Only some airports can accommodate. So we are hoping that once the gravimetric ratio is improved, then we'll be able to take more hydrogen and reduce the space requirement for this.
Nice. Thanks for that initiative and study towards sustainable aviation.
So it's a nice presentation. So one question from my side that how students can, if they want to start their own venture for, as you said, if they can create a technology to commercialization level, that will be better for the sustainability. So more ideas come, more students will think about the challenges. So can you suggest to the students how they can start from the institute level to create a technologies on the challenges, and what are the basic facilities or environment or ecosystem they need on the institute level in the campus, or they can do the POC on the ideas, they can draft their ideas on the hardware form or software form in the form, or so that they can test it on the market on the smaller segment level. So these are the things possible for the students on the ground level, or how industry can support to that students.
Anything is possible, So the issue is that first and foremost thing is that I would advise students to be extremely cautious if you're dealing with hydrogen because it's highly explosive. So we don't want explosion in the university for some student body. So you need to be extremely cautious and done under health and safety regulations. The second thing is you talk about commercialization. Now, at this point of time, hydrogen is very expensive. It's almost between 6 to 8 times more expensive than architecture. So I was talking to some students during the tea break, and I was saying that the technology is only as good as it can be implemented. Because if it cannot be implemented, it will just be put in archives as a very good thesis. And it will be only implemented if there is a commercial benefit to it. I think my colleague, Dr. Kishore, because he has been coming from industry, and he will agree with me that if industry does not see a value in that, where they can make money, it will not see the light of the day. So that is an important. So a route to commercialization is important, but initially it will be very expensive. Because hydrogen, if you want to commercialize it, the sheer cost of hydrogen is so expensive that in this room we all talk about sustainability and our support for environment. But we have to be very practical also. Let's say that today there's a flight from Bhopal to Delhi, and one flight is flying conventional fuel costing 5,000 rupees. And there is another flight which says that it is using hydrogen, but it is going to cost 25,000 rupees. I think we look at the pockets more than environment at that point of time because it's reality. So if you want that to, if you want people to fly the hydrogen aircraft, then somebody has to subsidize. So the government has to pay the remaining 20,000 pounds to encourage people to fly that. Because if you don't encourage people to fly that, there won't be demand created. And if there is no demand created, then the production will not be created. So currently the problem with hydrogen is that there is no demand for that. In the sense that in terms of real demand, there is demand for hydrogen in different ways. But in terms of commercial scale, you need to produce lots of hydrogen at a very cheap price. Now it is very expensive because to produce hydrogen you need energy. Now, how will you get the energy from? So that's why I was talking about nuclear and if you want to produce green hydrogen, all this is viable only if you're producing green hydrogen. If you're going to produce other forms of gray hydrogen, blue hydrogen, and so many colors of hydrogen, it's not going to be economically feasible because if you take natural gas, which is hydrogen, and if you break it into, for example, if you take methane and break it into hydrogen and carbon, it is energy intensive. So you need to spend energy to get hydrogen, which makes it more expensive.
Thank you.
Any other questions?
Good afternoon, sir. As you showed that there are some of major drawbacks for nuclear-based propulsion, but it is faster, and for space travel it is even 10 times faster. So what are the future possibilities of it for aviation and for space travel?
Space travel, there are more qualified people here to talk about the space travel. We are only talking below the space. In terms of nuclear, it is an option. But I told you that there are a lot of challenges to that. Because the word nuclear itself sort of scares people.
in real terms and psychologically also. So I'm not sure in our times that whether we will have these kind of things, but nuclear has enormous amount of energy if it can be harnessed. And somebody was telling that mobile with the nuclear, this morning somebody was saying that a mobile has been produced with a small nuclear device which will last for 50 years and does not have any, with no radiation. Maybe if some future technology comes like that, safer technology, that may be possible.
Thank you, sir.
So I have a question on implementation of hydrogen fuel. Like, how does it influence modern aircraft design, or it even changes the architecture of engines?
It's a very good question. In terms of the architecture of the engine, it probably changes only the combustion system because the rest of them remain, because it is a heat source. So you need to change because you need to have shortened combustion because of the properties of hydrogen, and also you cannot use it. That is why hydrogen is not a drop-in fuel like SAF. SAF is a drop-in fuel because you can blend it with kerosene or you can use it directly, or like biofuels. You can use them in blends because you don't need to make changes to the combustion chamber. Whereas in terms of hydrogen, because of the characteristics of hydrogen, you will not be able to use the existing combustion chamber. So we foresee that if you want to replace it to a direct combustion engines, the one component that will need a major change will be the combustion chamber. The remaining can, the rest of the components can remain the same because it does not affect them. Obviously, my colleague talked about contrails. Hydrogen produces lots of water, but it does not produce soot, which is a particle which by the contrail nuclei. So there are different challenges with using hydrogen, but yes, the existing engine can be modified to use hydrogen.
So another question, how long before can we see this fuel being used for civil aviation?
For my presentation, each one of the phases is between 20 to 30 years. So we are hoping that by 2050, we will have at least some form of flying using hydrogen. Because we are in 2025 now, so it's 25 years. 25 years in for these kind of transition technologies quite a less time. Because there is a lot more to do. Many of these studies, we have made a lot of assumptions in that, but a lot of serious studies are going on many aspects of hydrogen. So we need to consolidate all of them and go through the certification before it is actually commercialized. But yes, there might be some trial flights by airlines using this. We already had fuel cell, using fuel cells.
Thank you, sir.
Good afternoon, sir. I have a question about nuclear pulse propulsion. How sustainable it is?
To be very honest, I'm not an expert in nuclear pulse. I don't know if anybody else can answer this question. I think we'll leave this question for the experts in nuclear pulse propulsion. I'm sorry, I'm not an expert on this. I should not be saying.
Thank you, sir.
Sorry. No more questions? Thank you very much.
Thank you, sir. Now I would like to invite our conference chair, Dr. Prashant GK, to offer a token of appreciation and respect to Dr. Suresh Sampal.
Good afternoon, everybody. The session as planned after this would be specifically the tracks, but we are going ahead with it in the 2 o'clock session where we have the that is the session chairs. They are not occupied in any other additional work. So we are going with that very same track after 2 o'clock. So lunch break, we are breaking right now for the lunch break, and followed by this, we'll get back at 2 o'clock so that we can resume the other activities without delay. And I thank everybody for their session right now. Thank you.
Following lunch, that is the parallel technical sessions. We have displayed the topic and the venue of each of the technical sessions. I request the participants to reach their respective venues after lunch, and I request the audience to join the room as per their topic of interest. Thank you.
Please.